Here we are going to discuss the JFET DC load line and biasing techniques. Before that, we'll have here some notations used in the slide. The first one is drain source voltage, gate source voltage, drain current, pinch off voltage VP, and IDSS, maximum drain current at VGS equal to 0. K is a constant, that is a function of construction of device. With this, we'll move on to the topic. We know the transistor is classified into bipolar junction transistor and field effect transistor. So this bipolar junction transistor is a current control device, whereas this one is a field effect transistor is voltage control device. Here this FET is classified into junction field effect transistor JFET and the metal oxide field effect transistor MOSFET. Let us move on to the junction field effect transistor. So this one is already we have discussed in the electronic devices first semester itself. Let us move on to directly the operation of the JFET. Here this JFET is having three terminals: gate, drain and the source. So between the gate and the source we have here one voltage called the VGS, and between drain and source we have a voltage called the drain and VDS. Okay, these two things are applied into the JFET. What happens once if you are externally connected the voltages, we will directly discuss the drain characteristics and the transfer characteristics of the JFET. So what is the drain characteristics? So the diagram shows in the x-axis you are taking the VDS, in the y-axis we are taking the output current, drain current. So there are various steps to be discussed here. First one, if the VGS and VDS both the things are 0, so what happened? There is no drain current. So the drain current doesn't flow, so you will get the device is under the off condition. Next, let us move on to first one applied. The VDS is applied. So small voltage is applied at the condition of VGS, gate source voltage equal to 0. So what happened? If you slowly move on to the increase the VDS, note down the current value. So ID, the drain current increases linearly with the VDS. But you just note down, as VDS increases, that is the voltage drop across the channel also increases. This increase in voltage drop increases the reverse bias on gate source junction. So there is a change in the gate source junction and causes the depletion region to penetrate into the channel, reducing the channel width. That is very important. Next one, this effect of reduction in channel width provides the more opposition to increase the drain current ID value. So thus the rate of increase in ID with respect to the VDS, drain source voltage, is now reduced. So this is a important point in this drain characteristics. Next, another important point note down here, the pinch off voltage VP. Just look into this diagram. There is a VP as noted here. What is meant by pinch off voltage? Means the voltage VDS at which the current ID reaches to its constant saturation level is called the pinch off voltage. Wherever it reaches, whenever it reaches, so it is nothing but your pinch off voltage. Okay, so this is your first part. What happened when you go to the VGS value? So VGS is here I am applying, for example, VGS equal to minus 1 volt, negative biasing. So what happened means, so the gate channel junctions are further reverse biased, reducing the effective width of the channel available for the conduction. Because of this, drain current will reduce and pinch off voltage is reached at a lower the drain current than the VGS. Is when compared to the VGS equal to 0, here the value is reduced somewhat. So you just look into this, previously my drain current is equal to 8 at VGS equal to 0, whereas here drain current equal to 4 when VGS equal to minus 1 volt. So obviously it is reduced here. Next important one, breakdown region. So what is a breakdown region? Here further increment of your VDS, drain source voltage, automatically my voltage JFET becomes, that is voltage becomes constant and the current values are drastically increasing. So this region is nothing but your breakdown region. So don't operate the JFET under the breakdown region. This is an important one. Another important point is here there are two regions, ohmic and the saturation saturation region. What is a ohmic region? Means the drain current ID varies with the VDS initially, so that is nothing but your ohmic region. What about your saturation region? The drain current ID remains fairly constant and doesn't vary with the VDS. You can call it as a saturation region. Always operate your JFET under the active region. So repeat the same procedure for several VGS, positive value and a negative value. So most of the time you can give the negative value, analyze, so you will get the result. Next, coming to the transfer characteristics. So what is a transfer characteristics means? So if you increase the VGS value in the negative direction and note down the corresponding drain current. If you are increasing the negative value, obviously the current value is decreasing, ID current is decreasing. So this is a transfer characteristics of your JFET. Okay, so this is a revision of your JFET drain and transfer characteristics. Once if you analyze the concept, let us move on to the DC load line concept. So what is a DC load line? Means we are going to fix the operating point. Here VGG and the VDD are the input biasing and the output biasing. The same thing. Say here VDS and ID are the drain source voltage and the drain current. So here there is a resistance RD connected in the JFET. So what happens? So let us go to the Kirchhoff laws concept. Apply KVL to the figure 1. So your VDD is equal to, that is your applied voltage is equal to potential drop at JFET and the potential drop at resistance RD. From this apply that is if the condition ID equal to 0, what happened? Obviously your VDD is equal to VDS, and if VDS is equal to 0, ID is equal to VDD by RD. Here we have 2 points. So note down these 2 points and put it in the drain characteristics. So here in the y axis we have ID value VDD by RD. In the x axis we have VDD. So join these 2 points, we will get one straight line. So this is nothing but your DC load line. So apply the DC voltage, note down the values. Here this is nothing but your DC load line, and from this graph identify the Q point, that is operating point. So this Q point should be in the mid of the region. So this one is nothing but your DC load line and the biasing point. So operate the transistor under this Q point. So once if you are discussed the operating point and the Q point, so next we will maintain the operating point is a very important one. So the FET or and BJT are the temperature dependent. So whereas in the FET is a temperature increases, drain resistance also increases, reducing the drain current. Thus unlike a BJT, so thermal drive doesn't occur in that FET. So keep in mind, this is one of the advantage. However, wide difference in the maximum and minimum transfer characteristics make it necessary to keep, that is very important, drain current ID stable at the operating point quiescent value. So in this slide we are giving a different biasing techniques, JFET biasing techniques to maintain the Q value. So there are 3 biasing techniques using the resistor technique, using resistive elements: fixed biasing circuit, voltage divider circuit and self bias. So for this the general relationship can be used for the DC analysis. So IG equal to 0 amps, ID equal to IS, ID is equal to 1 minus VGS by VP the whole square. For MOSFET, ID is equal to K of VGS minus VT the whole square, where K is a constant. Already we have derived, this is a formula. So let us move on to the first one, fixed biasing. So here the fixed biasing is nothing but there is a small voltage is applied to the base terminal. So that is RG is connected to the base terminal and your RD are connected at the top in the drain terminal. So there are 2 capacitors. For the DC analysis, these two capacitors are open circuited. So this is a simplified circuit diagram of your fixed bias circuit. So let us move on to the DC analysis. Here first one, for already we have discussed Ig is equal to 0 amps. So apply KVL to the input circuit. VGS plus VGG is equal to 0. So VGS equal to minus VGG. So one thing, VGG is a fixed DC supply. VGS is a fixed in magnitude. That's why it is called a fixed biasing circuit. So for the drain current, because your Q point is depends upon your ID and the VDS. So find the ID according to Shockley equation. IDSS into 1 minus VGS by VP the whole square. What about your VDS? Apply KVL to the output circuit. Your drain source voltage plus IDRD minus VDD equal to 0. From this, VDS equal to VDD minus IDRD. So let us move on to the problem, then you can easily understand the equations. So from the given diagram, that is for the given circuit, find the VGSQ, that is operating point, IDQ, current at the operating point, and VDS and the VS. So let us go to the first one, VGS equal to minus VGG. How to get this equation? From this above discussion, VGS equal to minus VGG. So which is equal to minus 2 volt, the value is given. What about your ID? ID is equal to IDSS into 1 minus VGS by VP whole square. We know this equation. So VGS value is given, VP value is given, and IDS is equal to 10 milliamps. Substitute ID is equal to 2.5 milliamps. Next, what about your VDS? VDS is nothing but VDD minus IDRD. So your substitute the value. ID just now we have found, RD is value is given, and VDD is given applied voltage. So your value is found. Next, what about your final one? VD. So VDS plus VS. So VS is, there is no VS value here, so which is equal to 0. So automatically 5.5 volt. So that's all about your fixed biasing. Next we will move on to the voltage divider biasing. So voltage divider means here two resistors R1 and R2 is a potential divider, gives a constant voltage, and it will compensate for the or it will maintain the Q point. So if Ig, again coming to the DC analysis, Ig equal to 0. So what about your VG? VG is nothing but input voltage to the gate, opposite resistance by some of the two resistance into the your VD applied voltage. So apply KVL to the input circuit, and VG minus VGS minus VS equal to 0. So from this, what about your VGS? VG minus ID into RS. VG is total resistance value. So apply KVL to the output circuit. So VDS equal to VDD minus ID into RD plus RS. So take the one problem for the given circuit. Again we will go with the same concept. So everything is given. So VGS is equal to VG minus IDRS. What about your VG? The equivalent value. So your R2 divided by R1 plus R2 into VDD, which is equal to 4 volt. What about your VGS? 4 minus ID into RS. That is VG minus ID into RS. VG already we have found. What about your ID? It's an unknown value. So ID is equal to IDSS into 1 minus VGS by VP the whole square. So we are getting a second order equation. How to solve second order equation? By means of quadratic equation. So by solving the quadratic, ID equal to 5.3 or 3 milliamps. So if you take 5.3 milliamps, our VDS is equal to negative value. So practically it is not possible. So we can go for the another ID value, 3 milliamps. So if you substitute the ID is equal to 3 milliamps, we are getting the VDS equal to 2.4. So what about your VGS? Your VG minus IDRS, which is equal to minus 2 volt. So we know VGS is a negative value. So what about your VS? ID into RS, which is 6 volt. So that's all about your voltage divider. So if you know the concept of R1 and R2, you can easily solve the problem. So next, finally, a self-bias circuit. Self-bias is nothing but one resistor, that is your RS resistor gives the supply volt, gives a constant voltage to the gate terminal. So that will maintain the Q point. So so next one, your two capacitors are in for DC analysis. It is open circuited. So simplified circuit of self-bias. So there is a feedback applied to the gate terminal from the RS value. So apply KVL to the input circuit, minus VGS minus VS equal to 0. So your, what about your VGS equal to minus VS IS into RS, minus IS into RS, which is equal to minus ID into RS, because IS and ID are equal. So we know ID is equal to IDSS, Shockley equation. So substitute in the ID value, we will get IDSS into 1 plus IDRS by Vp the whole square. So apply KVL to the output circuit. We have VDS equal to VDD minus ID into RS plus RD. So keep in mind VDS, ID are two important factors to maintain the Q point, operating point. So let us move on to the problem, self-biasing. So everything is given. So our ultimate aim is to find the ID value. So ID is equal to IDSS into 1 plus IDRS by Vp the whole square. Substitute. We will get the second order equation. By solving the quadratic equation, so ID is equal to 8 milliamps or 2 milliamps. Note down, your given IDSS is 8 milliamps. Okay, so the actual value ID is equal to from the second quadratic equation value 8 milliamps. So these two things are given is IDSS is 8 milliamps, actual value is 8 milliamps. So if you take those two values, it is not possible, it is invalid, because ID maximum saturation current is 8 milliamps is a given. Okay, so you cannot go with the first one. So definitely the second one, ID is equal to 2 milliamps. So VGS equal to, substitute ID is equal to 2 milliamps. So find the VGS value. Next step, find the VS equal to ID into RS. ID already we have 2 milliamps. What about your VDS? VDD minus ID into RD plus RS. So finally we have VD is equal to VDS plus VS. So that's all about your self biasing of JFET.